Thank you very much for the invitation to talk in this conference. And I'm going to be talking about Particle-Soliton degeneracy into the QCD, which is basically mostly based in the work of this last year in these 3 papers with Clay and Nick, who's a junior graduate student of Clay. And okay, so just to begin with motivation, well, we know that gauge theory is basically of extreme importance to understand nature. We have known that for half a century now from the standard model of particle physics. And as we all well know, QCD is very difficult to understand because of asymptotic freedom. So at very high energies, it is weakly coupled, well understood. We can do Feynman diagrams and we can do many things, but the low energy regime is mysterious to this day. We don't understand very well what's happening at low energies when the coupling becomes strong. And well, we basically do not understand why QCD is trivially gapped, why it has a single ground state. So based on this observation, it's valuable to gather intuition about QCD from studying related models, in this case, lower dimensionals, to gather intuition about the strongly coupled gauge theory. Well, what I just said. And recent advances tells us that non-invertible symmetries help understand important properties in quantum field theory, like confinement, vacuum extraction, and spectra, which is going to be the subject of this talk. And we're going to characterize the spectrum of 2D QCD theories when the theories are capped. So before getting to 2D QCD, let me start with a pedagogical example that will essentially have all the properties that we will be looking for. And to begin, let me introduce some key concepts, basically like what do we mean by a particle and a soliton, which are 2 different qualitative type of excitations, where a particle is essentially an excitation of a field that interpolates between like the far left and the far right into the same vacuum state, while a soliton interpolates between 2 different vacua. So in classical field theory, these are 2 very different type of excitations. For example, if you have a small coupling, then particles are very light, as we know from quantum field theory, while solitons are very heavy. And because of this difference between the vacuum state to the far left and the far right, we cannot basically continuously deform from one state to the other. This requires changing a boundary condition at infinity. So these are 2 different qualitative type of excitations that we all know and love from our textbook quantum field theory. So the pedagogical example that I want to bring to the table is essentially the tricritical Ising model deformed by the 5-to-1 deformation. If you are not aware with, or you are not, well, if you don't know about the abstract 2D CFT, you can just basically think of this as a Landau-Ginzburg model with this potential, which in particular notice that it's not reflection symmetric, so it's not quite the type of potential that we study in textbook quantum field theory. And as a statement, the spectrum is gapped, and there are 2 ground states. Now, why is this model interesting? Thus far I have just shown you potential. Is because this model can actually be solved exactly by integrability. We can bootstrap the system, and we can actually find the spectrum and the scattering S matrix exactly. But here, mostly we care just about the spectrum, and we are going to find that, as we expect, there is one soliton and anti-soliton. But more importantly, there is a single particle on one vacuum only, on one of the potential. And interestingly, the exact solution shows that the particle and the soliton have the same masses. So the question that I would like to raise is, can we have a natural interpretation of this phenomenon? Could we have predicted that this would have happened without having to actually solve the full system, right? So how do we see that? Well, as I said in the introduction, it's going to be because we're going to consider this novel form of symmetry, which arises from the work of Gayotto, Kapustin, Seiberg, and Willett from like 10 years ago, which proposes that we should not understand symmetries based on group theory, but as we usually learn in physics, but basically in the existence of physical excitations that can be, that are topological, that I can deform with no energy cost. So the textbook example is the exponential of the integral of a current. So if I do a small deformation, then that doesn't change any correlator, and that we consider a symmetry. So we're going to take this property as a symmetry in general, and it can be that a given such defect has an inverse that gives you 1, But more generally, it can be some general linear combination with some integers. So there are other ways that invertibility can be broken, but for the purposes of this talk, everything will just be this linear combination of defects. And mathematically, this is described by something that is called a fusion category, but I'm not going to get into that. All you need to know really is that when I fuse two of these topological defects, I can have this linear combination of integer linear combination of defects. That's really all you need to know. Well, one reason why we have the right to call these symmetries is, well, they basically have the same properties that you expect from a symmetry. They can be spontaneously broken, imply energetic degeneracies, gauged if non-anomalous, and constrain energy flows if anomalous. Okay, so that's the tool that we're going to use. And from the paper by Cheng Chang, Lin, Xiao, Yifan Wang, and Jin, we know that actually this flow of the three-critical Ising model by the 5-to-1 deformation actually preserves one line from the CFT in the UV. And it has this fusion rule. So it's non-invertible because you have a second element here. So the flow has a non-invertible symmetry along the flow at a finite energy. And the statement is that the infrared, because the theory is gap, we can think of this as some spontaneous symmetry breaking of this non-invertible symmetry. And what we're going to do is basically to define different Hilbert spaces with different boundary conditions at the left and the right. And in this case, because the symmetry is spontaneously broken, basically these boundary conditions to the left and to the right. Like we have, here I have drawn in a finite interval, but we should think of this as the infinite left and infinite right, quantizing the theory on a line. And in our case, these labels are going to be 1 and W, which are basically the symmetries of the theory. And we can see here that we can interpolate from one Hilbert space that has 1 and W at the left and the right to a Hilbert space that has W and W. So this is basically something that we will have called a soliton, something that interpolates between two different vacua, and WW, which is just a state in the very same vacuum. So we can see here how a topological line can basically interpolate between two different of these Hilbert spaces, one which will be solitonic and one which is more particle-like. And studying basically the effect of the symmetry on these boundary conditions, we basically reach the conclusion, or we can encode, summarize the different relations between the Hilbert spaces by saying that if we have, by putting the vacuous nodes and the possible interpolations with lines, with directed lines, and we will see that we will have two solitons, so one state from 1W and W1, and also one state in WW, which is something that we don't see with invertible symmetries. And this is basically related to the idea that we can have multiplets of states relating particles and solitons in 2D with non-invertible symmetries, which is in this paper, where basically this example is worked out in detail. So this is essentially the type of thing that we are looking for. And we want to see this in the context of a gauge theory, such as QCD, which is not as easy because it's not it's not, you know, a minimal model deformed by an integrable deformation. It's more complicated than that. And my goal is basically to tell you that, for instance, in this SO3 with fermions in the 5 and PSG4 with fermions in the 15, these directed graphs are going to be basically the analog of this graph for the three-critical Ising model, deformed by 5-to-1. Okay, so first, let me remind you that in the modern paradigm of renormalization group flows, we start with a UV CFT and we flow to an infrared. And the theory in the infrared can be gapless, described by a CFT, like Maxwell in 4 dimensions. Or it can be gapped. And in the case that is gapped, we furthermore want to distinguish between two cases. One where the theory is trivially gapped, meaning that the infrared is totally empty. We have a single ground state, nothing too interesting going on. And the second case, which is going to be the case that we actually care about for the rest of the talk, which is topologically gapped, meaning that there are not real topological degrees of freedom in the infrared. And we can have topological correlators, we can have different vacua, and we care about this so that we can actually talk about solitons. So we can have different vacuum states to the far left and to the far right where we can, in which we can interpolate. So the theory that we're going to consider is massless fermions. So it's basically this Lagrangian with no mass term for the fermions. One such example is adjoint QCD, which we heard from Silvio this morning. And as he said, an interesting thing about this model is that despite the fact that there is no, in the adjoint case, despite the fact that there is no mass term, the theory develops a gap. In the adjoint case. And now to be more precise, we are going to bosonize and consider 2D QCD as a gauge WCW model with matter content given by this Wess-Zumino-Witten theory and gauge fields for the group G and kinetic term for the gauge fields. So in the UV, we have 3 fermions. In the infrared, we have some gauge WCW model. And this, we do not lose any generality in principle because of the, we can always invert between fermionized and bosonized theories. So in principle, we can always translate in between one and the other. So for the rest of this talk, I will really be talking about the bosonic version of the theory. Okay. So because we care about constraining Particle-Soliton degeneracy, we are going to focus on gapped 2D QCD theories so that we can isolate any possible gapless modes. We have a discrete set of vacuum states and we can interpolate between them. And essentially what we want is to describe the low energy regime of this theory, which was, we want to describe the low energy regime of this theory. And for that we need to know when a 2D QCD theory is gapped or not. It turns out that this question was answered by Del Mastro, Gomis, and Yu a few years ago. And the gap criterion is actually a rigorous criterion, which says that the theory is gapped if and only if the corresponding coset has vanishing central charge. And the central charge of the coset is actually just the difference of the coset of the Wess-Zumino-Witten theory associated with the numerator and the denominator, where IR is the index of the representation R that we have chosen for the fermions. So if we have fermions such that this difference of central charges is 0, the theory is gapped. If not, then the model is gapless. We care about those models that are gapped. So we wish to study the action of non-invertible symmetries over vacuum, and for that we're going to use, therefore, the infrared. We have this topological coset, which is essentially an algebraic version of the gauge WCW model that I presented before, that I showed before. Okay, so how are we going to use the fact that there's a topological coset? We're actually going to invoke the fact that we can study 2-dimensional theories from a 3-dimensional theory. So the first version of that, maybe the best well known, is the fact that we can study Wess-Zumino-Witten theory based on a group G at level K from a Chern-Simons theory at group G at level K. And then we can impose appropriate boundary conditions to the left and to the right, and we can recover the 2D theory from 3 dimensions. That's a standard construction. A little bit less known, but basically in the same spirit, is the fact that we can study cosets by putting coset GK over HK tilde, by studying GK with HK tilde reversed. And instead of imposing the Dirichlet boundary conditions for each gauge field in the GK, we impose boundary conditions that basically tell us how HK tilde embeds into GK. And the statement is that that will give us a 3D construction for the 2D coset theory. Now, why is that important for us? Is because this is the way that we are going to essentially describe the topological cosets in the case when the central charge is 0, right? So in the work of Moore and Seiberg, they basically tell you how to do this, but it's basically for the gapless case. They do not consider gap boundary conditions, and they don't quite say it in those words, but it's essentially that. Okay, so the main tool that we are going to use is that to take the proposal of Moore and Seiberg and allow for the boundary conditions in the left and to the right to be topological boundary conditions of the bulk 3D TQFT. Namely, boundary conditions that I'm free to move around, which is something that has been studied by condensed matter physicists for the past decade, 1-2 decades. So that's the essential tool that we're going to use in this HEPTH context to study topological cosets in the far infrared and see how non-invertible symmetries can act over vacuum. So basically the fact that the observation that topological boundary conditions are a thing is basically what allows us to have something like a Moore-Seiberg framework for gapless cosets and topological cosets. And it turns out that this is always possible. Topological cosets always allow for such a boundary condition, which is something that has been argued by mathematicians well, in these two papers that I know. So it's mathematically grounded. We can always expect this for any topological coset. This is always the case. Good. So basically what I have to explain to you now is how to set up these boundary conditions for a given 3D TQFT, and how we're going to use that to say how non-invertible symmetries act over the vacuum. So, okay, I don't want this talk to become basically a talk on 3D TQFTs. So let me just have this one slide to tell you how to basically deal with 3D bulk TQFTs, which is basically tell you that 3D TQFTs are basically theories that consist of topological line operators that we call anions, mathematically described by modular tensor categories. Again, you don't need to know anything about tensor categories. What you need to know is that this set of lines fulfill a finite set of data, such as fusion rules and a modular S matrix, describing the braiding of one line over another one. And all of this data can in principle be obtained. We will mostly be working with Chern-Simons theories because of the previous slides, what I explained before. And all of this data can essentially be recovered from the corresponding Weston-Minowitten theory in case you are more comfortable talking in 2D language. So that's really it. It's basically a finite set of data from which you can compute any correlator. And what we want to study is basically topological boundary conditions of these 3D theories. So to do this, so this is a number of statements that are true, which is that any topological boundary condition of a 3D TQFT is described by a linear combination of anions called Lagrangian algebra. So basically an object of this form. This Lagrangian algebra has a very compact physical interpretation, which is that they are the anions that can end at the topological boundary, basically as in this figure. So if A belongs in the Lagrangian algebra, then it can end at the topological junction at the topological boundary. Now, here comes an important observation, which is that topological boundary conditions of a 3D TQFT are always endowed by an associated fusion category. So basically, some non-invertible symmetries living at the topological boundary. And from the 2D perspective, these F are topological lines are going to be symmetries of the matrix 2D QCD model. And actually, in the context of cosets, there is a very natural candidate coming from the branching rules. So I'm not going to explain this in detail, but basically, if you know the branching rules, then you know the Lagrangian algebra. So you know the proposal for what are the line operators that can end at this topological boundary. Now, in condensed matter, this is a process that is called anion condensation, where we where we condense essentially this anion on half of space-time, and that basically goes at a topological boundary condition for the theory that here I have called C. And in high energy language, this is something that we could have said that you are gauging a generalized symmetry on half of space-time to develop these topological boundary conditions. This corresponds to inserting a mesh of some symmetry, some gaugeable object on half of space-time. At any rate, these are basically the ingredients, the main ingredient that we need to characterize topological boundary conditions of 3D TQFTs. And how to find basically an associated fusion category in the theory, in 2D QCD. This is basically going to be the analog of the W that I mentioned in the pedagogical example earlier. Good. So how are we going to find this fusion category? Essentially, the statement is that if we take any line operator of the full 3D TQFT, which is our product of Chern-Simons theories, we can basically push the line to the boundary. And this will basically split the bulk anion and become into a linear combination of simple or line operators of the fusion category of the 2D theory. So there are a bunch of conditions that the fusion ring has to satisfy. You don't have to learn all these rules just by looking at it, but you have to know that certain consistency conditions exist, and that basically like anions that are in the Lagrangian algebra always have, when they split, they always have a component to the trivial line, which is important to basically put these ingredients here to work out the final fusion ring. So that's basically an algorithm, if you want, or a setup to start with the Lagrangian algebra and find a fusion category at the boundary. Find fusion ring of the 2D boundary by splitting rules. Now, having found the fusion category, the fusion ring, We can also talk about local operators. And the topological local operators by the state operator correspondence are basically like every local operator will give you one of the vacuum states. So from that observation, we can basically see how fusion categories will act over the vacuum of the theory. And therefore, we will be able to make the analog of like how the W line acts over the 1 W in the picture back ago in the pedagogical example. We will be basically able to find the analog of that by acting with the lines of the 2D theory over the vacuum constructed in 3D by stretching an anion in the bulk from one topological boundary to the other. And once we know the boundary condition, we can ask how Hilbert spaces defined by different boundary conditions are related by the action of the non-invertible symmetries explained before. But now it will depend, of course, on the specific fusion ring, on the specific vacuum that we find, and so on and so forth. So there is a very general story that was written by Clay, Cantaro, and Nick in this paper from a few months ago. So we will not need the general story here. Actually, for our purpose, it's going to be much easier. And we are going to encode the degeneracies in a quiver diagram, in a directed diagram, as I showed before, where for each topological local operator, we write a node, a vacuum. And irreducible representations of the non-invertible symmetry are going to be labeled by the lines A of the fusion category. And we write n, blah, blah, directed arrows from one vacuum to the other, where n are going to be the fusion rules of the fusion category that we find by pushing the lines of the bulk to the boundary. This is something that is reminiscent of that I first learned from the paper of Ceccotti and Baffa on n equals 2 supersymmetric field theories. That was basically the initial observation to see that we can encode the degeneracies by these quiver diagrams. So, okay, let me finally say some things about 2D QCD. So I have said here many things. So let me first give you like a summary of the steps for 2D QCD, which is first start with a 2D QCD theory that is gapped. As I told you, this is just a criterion on the central charges, and those are completely classified. So the full table of theories are in Del Mastro, Gomes, and you, in case you want to take a look at all the theories. So we take as bulk Chern-Simons theory, this basically a spin, which is the matter field for us, and GIR describing the gauge group. Now this is for simply connected gauge group. If you take a non-simply connected gauge group, you have to divide by something that is the common center or some abelian symmetry in the product. This essentially what it does is to take us from the theory with multiple universes to a theory that has just one universe, where all the excitations are going to be finite energy, which is what we care to relate here. As Silvio Pufu explained this morning, where we have many universes and we just want to study just one of them. But in bulk, this means that there is a common gauging that you have to do. And it's what I'm going to be doing. So basically the steps that I'm writing here basically are the same, but for this product instead of this other product. So set coset boundary conditions describing the conformal embedding from G to spin, DMR. And basically use the technology of Lagrangian algebras and Arnold condensation to read explicit 2D fusion category at the topological boundary, and therefore the action over vacua or local operators, whatever description you prefer. And from there we can basically we can set up basically boundary conditions corresponding to the vacua at the far left and the far right, and we can study Particle-Soliton degeneracy. So one such example is SO3 gauge theory with fermions in the 5. So again, the non-simply connectedness comes from the fact that I want to study a single universe. So I gauge by a common C2 symmetry. And I find at the boundary a fusion category that basically has a C2 symmetry, but an additional line that has this interesting fusion rule. Good. So we have 3 vacua with 3 reducible multiplets, and each vacua I'm going to label it, we label it with one symmetry element. And so we find, so we have 3 multiplets. One of them is basically what you expect, which is there is always a multiplet that there are only particles in each vacuum. We also have a multiplet that basically is like a C2 symmetry that relates one vacuum with the other, and then just a single particle in the third vacuum. So nothing interesting there. But we have this interesting multiplet, where we have, similarly as in the tricritical example, where we have one particle with the same mass as Soliton anti-Soliton pair. we will have two anti-Soliton and Soliton-anti-Soliton pairs connecting the vacuum 1 and V to A. And on top of the A vacuum, we will have two particles with the same mass. So we will have something like a six-fold degeneracy in this multiplet. And actually, because if we require a non-empty Hilbert space, then that means that there should be a non-zero Soliton state here, and that the states in this quiver must exist. They must be present in the theory. So another example that we can study is SU4 with fermions in the adjoint SU4 projected to one universe, so it's PSU4. So this is the cosset TQFT, and we can study topological boundary conditions, we can study the boundary fusion category, and now we find that there are 4 vacua. The fusion category has the lines 1, B, A, and B with this fusion rule. So V again is a C2 symmetry, and we find these interesting fusion rings. And now, well, we also have the two multiplets similar to this one and this one, which are kind of boring, but we will also find two other multiplets, which are more interesting. And in the same vein, we can see that certain excitations have to be in the spectrum, which in this case are excitations that connect the vacuum capital A and capital B in between them. And there are going to be particles in the vacuum A and particles in the vacuum B with the same mass. And this must belong into either this multiplet or this multiplet. Which one, I don't know, because that's a question of dynamics, not of symmetry. But they have to appear in either one of these multiplets. Good. So these are basically the examples that I wanted to tell you about based on the previous strategy. So let me just summarize what we have done here, which is basically using non-invertible symmetry to constrain the spectra of gap-2D QCD theories. In particular, we have seen that non-invertible symmetry implies mass degeneracies that are novel, that are not quite what you see with a standard group-like symmetry, which relates the mass of particles and solitons. We have also seen the importance of appropriately taking into account topological sectors in 2D QFT to understand finite energy physics from the 2D topological concept, and not saying that basically the theory is trivial just because there is no gapless modes. And we have also seen the practical use of Fannian condensation to derive a specific fusion ring in 2D QFTs, or, well, also gauging non-invertible one from symmetry in a high energy words, which was basically our main tool to derive the fusion rings in 2D QCD. And now let me finish with a few future directions, of which I wrote many. So first, extend analysis to other 2D gauge theories. So a similar story, one can sit down and try to study a similar study for other theories. Other applications of 2D topological concepts, something, so here I basically use 2D topological concepts circumstantially in the context of 2D QCD, but of course, topological concepts appear in many other contexts, like the G over G model appears all the time in physics. So it will be interesting to use this technology to see what G over H can say in other contexts using this algebraic machinery. So I know there are many lattice experts in the audience. I'm certainly not one of them. But something that I would like to see is basically this Particle-Soliton degeneracy that I have just talked to you about by direct calculation. That's something that would be very nice to see. I should say that in the tricritical Ising model that I mentioned in the beginning, I believe there are lattice models that actually point out to that degeneracy that people have studied. So if that's possible in 2D QCD, then great. Now, saying something, of course, some gap 2D QCD theories come in infinite families, such as adjoint 2D QCD. So it will be interesting to see some pattern in those infinite families. Here I have basically shown you the examples that I can work out with, pen and paper, so that I can understand conceptually each and everything that is happening. But it will be interesting to see, maybe using abstract mathematical machinery to see if there is any pattern in any of these infinite families. Next, constraint dynamics of 2D QCD with non-invertible symmetries, because those I have just told you statements about the spectrum. And of course, we know from Bootstrap, for example, that sometimes symmetry can constrain the fullest matrix. So it will be interesting to see what we can say about dynamics from non-invertible symmetries in the context of 2D QCD. And finally, of course, this is all in 2 dimensions. It will be interesting to see what's happening in higher dimensions. Like I don't know much about, supersymmetric gauge theories in 4 dimensions. So it will be interesting if there is some relation between tensions in domain walls from non-invertible symmetry in 4D, I don't know. Basically, how all this story generalizes to higher dimensions. If there is something to say about monopoles, I don't know. Okay, thank you.
Thanks for a very interesting talk. We have time for questions.
I had a following question. You talked about integrable model.
In the critical Ising model.
Sure. What is the simple integrable model? Two questions. It remains integrable if you change coefficient slightly. Does it remain integrable?
Sorry, can you repeat?
Does it remain integrable if you change slightly the coefficients?
Sorry, you mean when I change the deformation, or?
But you wrote a model. You wrote a
potential
with very explicit.
Yeah, it's the critical Ising model deformed by the phi to 1 deformation, and that remains integrable as far as I know for any value of lambda, which is what.
So this can you change 10 to the 11? It doesn't remain integrable if you change the coefficients.
I think so. Yes.
Yes.
I think so. I mean, if you pick lambda.
Okay. So that's basically.
You can change lambda, but not the 10 and the 12 and so forth. You need the
Oh, that's the question. Yes. So sorry, this value of the potential, I picked it up. I handpicked to reproduce what you obtain when you when you work algebraically with the critical Ising model, and you deform by the phi to 1 deformation. So this has been handpicked to reproduce what you obtain by the working abstractly with the CFT deformed by phi to 1 in conformal perturbation theory, if you want. Or, yeah. So you shouldn't take this potential that seriously.
So in which sense this model is integrable? In which sense this model is integrable?
Right, in that, yes. The statements that I have made here are essentially not really a statement of. If you want to take this statement seriously, you have to think about the actual critical Ising model deformed by lambda phi to 1 instead of this Lagrangian model.
Thank you.
Thank you. Other questions? Okay. I saw your hand first, but then there's a question.
Sure. So can you visualize in some way these solitons you had in gauge theory? So is it like, can I draw basically a bunch of fermions connected by some flux tubes? Is that a good picture for the states? And if yes, like how many? Oh, that's too naive. Well, I mean, I thought in 2D QCD all states are roughly.
Yes. Well, the thing is that in 2D QCD, maybe I should ask instead of stating, which is how do you separate like the flux tubes that generate different universes from different vacua? Because these are vacua, these are not universes. So if I understood correctly from Silvius,
I call off these flux tubes. I mean, to me, I do not know if there is some vacuum, just some flux tube and some representation filling in the world. Okay.
I see. Well, I would say that I don't have really a better picture other than, saying abstractly that maybe you can do it if you talk about the vacuum expectation values of the local operators that survive in the IR. Okay. And I can characterize the vacua from those expectation values. That I can do. I have not talked about it here, but you can do that. And you can see that you have like condensate of a fermion bilinear, or a spin field, and things like that. And if they are 0 or 1 or.
Maybe I could ask that, okay, you mentioned adjoint QCD a little bit, but do you have any guess how this, do you have any, like, you expect that there will be some degeneracies in adjoint QCD? And how would states
For general adjoint QCD or for PSU4?
Well,
for general, I don't have any statement of what I can say in general.
For general gapped, you don't have any statement. I mean, you said that.
For general, I don't have any statements, but again, like if you want a picture of more or less what these vacua do to the local operators that you can do in this example, for example.
So can you roughly say I want to translate this picture in more like some, at least cartoon of, some quarks connected by flux tube, like mesons, whatever, like, okay, you can visualize a meson, right, with a fermion connected by some flux tube. So is there a similar picture like this, at least?
You can give an expectation values to fermion bilinears, if that's what you're asking. That's certainly true. I don't have the values here, but I can show them to you later. You can certainly do that, and you can also do that with more abstract fields, like spin fields and things like that. That you can do.
There was a question from Truman next, and then I saw Igor, and then...
I have a rather obvious question. I'm sure you have thought about it. So you mentioned one of the future directions to be generalized is to higher dimensions. But then so in your talk, you relate particle to soliton. To go into higher dimension, you want to relate particle to some extended objects like domain walls. But then the domain walls have tension, right? And tension doesn't even have the same mass dimension as the particle mass. So I'm just curious, what do you think would be the result?
So that's what I wrote here, basically domain walls, just to make sure that, in principle, what I will expect just based on this work is that I will relate tensions of different domain walls of the same dimension. It's because as you say, like, how are you planning to equate like an energy to some domain wall? So a priori I will say yes. I don't have any reason to expect any relationship between like the mass of a particle of a localized object and a domain wall. So a priori, I will just say I will expect relations between tensions of domain walls and not of different codimensions, of different dimensions. Of course, maybe I can prove it wrong by higher category theory and things like that, but I don't want to make any statements about that.
Okay, thank you.
Yeah, just a comment on Victor's question, which this topic was already mentioned in Grisha Tarnopolsky's talk, but at theta equal pi in the Schwinger model, in one flavor Schwinger model, there are these half asymptotic particles that what Coleman called half asymptotic. It's just a fermion that interpolates between two values of electric field, and that's actually the soliton in the bosonized picture. So just a single fermion at theta equal pi is the soliton.
So there is a picture in this model.
I can't say I completely understand this, but I think I understand Coleman's picture, and just one fermion is dual to the soliton in the bosonized.
Rick, I think you were next.
Yeah, this may show that I don't understand your talk at all, but you can get to the tricritical Ising model with an even potential, right? Just phi 6, phi 4, phi squared.
Yes, that will be the 513.
Right, so that can get to the same tricritical Ising point, correct?
Yes, that has the same UV tricritical Ising point.
Yeah, so it's in the same class. So is this somehow got another handle that it makes it more analytical? So is that the point? Or could you apply it to that potential as well?
You can also apply to that potential. That's actually another of the examples that we work in the paper that I mentioned here. So sorry, let me show the reference. Yes, so in this paper, we basically work this example, which has particle-Soliton degeneracy. The other example that we do is that potential that you mentioned, which that's the 513 deformation in terms of the 521.
Yeah.
That has a degeneracy. That's actually how we realized that there was this general degeneracies in 2D quantum field theory, which is that Samolotchikov, I think, was the one who derived that in that deformation. You have, when you flow from the nth minimal model to the nth minus 1,
yes,
there is one, but for positive coefficient, it takes in between minimal models. For the other, it takes you to a gap phase. So when you study that flow, it turns out that from the nth minimal model, you have 2n degeneracy of solitons.
So
and you can apply that machinery, and you will rederive that degeneracy that Samolotchikov.
And you can use the same non-invertible language to study that model.
Exactly, and you can see that there are some non-invertible symmetries preserved, and you derive exactly the same degeneracy that Samolotchikov obtained in the 80s, I think.
Another question?
By directly solving the model, of course, not using. It has a Z2 symmetry, so it's. Yeah, you have C2, but you have a 2n-fold degeneracy. general.
We have another question. So
Maybe I
Theo?
missed this, but in this like boundary condition construction, is the symmetry you get is always faithfully acting, or could there be like a SPT kind of thing?
I think in general you can have an SPT, you can have more general things. I basically was, that's basically the comment that I meant. Sorry,
But I guess like in a given theory, how do you know?
This is the fact that things have become very easy is because of the fact that you have a conjecture of quantum infrared, which is the topological concept. Okay. Right? If you deform, for example, by you go to a gap to the QCD theory, by a mass deformation or like whatever deformation you want, you in general won't have that, and you can have more general things, of which I have no handle. Basically.
So, okay.
Sorry, a naive question related to the earlier question about picturing in terms of flux lines. Is there a simple picture of why the vacua correspond to the symmetry generators?
Well, that is, I would say it's the same answer that I just gave Theo now, which is, that basically comes from the fact that it's a topological concept with the two boundaries in the same boundary conditions. So basically the local operators are labeled by the same, you can label them by the same labels.
If you deform the theory by some other operators, I guess you break this symmetry?
Yes, generically, yes. Of course, it will be interesting to see deformations that preserve symmetry and study that, but in general, you will break symmetry.
I'm going to abuse my position to ask one question. I think it's very quick. Why 4-color QCD and not 3-color QCD?
Because in 3-color QCD, when you do the C3 gauging,
yes,
the symmetry that you obtain is basically invertible.
Okay, thanks.
That's it. Oh, more questions.
Yeah, thanks. So, so in your simplest example, I guess like the particle living in one of the wells just decays, is unstable to decay to soliton and anti-soliton. No, in the the very first example you had, like with just two well potential with criticalizing mode. Yeah, so like the.
Oh, that's all stable. That's like you can.
That's unstable to decay into soliton and anti-soliton, right? So
no,
there is
no.
There is no particle in one.
Yes, but no. That
So if I had an excitation around the vacuum one, it would decay into.
Oh, yes.
Yeah.
But
so,
I should say.
Okay, so that's not.
Sorry, are you talking about this specific model, or are you talking about models with this symmetry?
Okay, let's talk about this specific model for a second.
In this specific model, there is no such excitation other than the vacuum state.
Well,
you can work it out exactly. That's what homological did, or Cardi. That's what I'm saying. You're picking a model with the same symmetry?
Okay, let me get to my question actually. So, I'm sorry. So if so here you have a degeneracy between the mass of the soliton and the mass of a particle. So if instead I have a degeneracy of a mass of a particle with like mass of the soliton plus anti-soliton, so that my particle would be marginally stable to the decay to the soliton and anti-soliton. So at that point, would I have something interesting? So I'm asking this because I have in mind curves of marginal stability in supersymmetric field theories, where you have when you cross this curve, initially might have a stable particle, but heavy solitons. But on this curve, this particle becomes exactly.
Are you asking if all these states have to be one particle states, or?
So I'm asking if if I tune this potential in some other way, so that I do not have particle degenerate with a soliton, but I have a particle degenerate with soliton plus anti-soliton configuration. So that particle would be marginally stable. It could decay into soliton, anti-soliton, and vice versa. So would I have some enhanced symmetry in that point?
Sorry, maybe I don't understand your
question. Maybe we should discuss later. That's
I would say if the solitons have the same mass of the particle, then that will not happen.
Okay, so I think the two of you should discuss later. This sounds very interesting, and I'd be interested to know more myself. I think we're out of time, so we should move to Yuya's talk. Let's thank Diego again.